Sure. Oh, wait, no, this part. Because I have the Zoom, I'm checking, that's not this one. Let's try it one more time.
Yeah.
Um, no,
Oh, you're not able to fully protect it.
yeah, now I need to come to this screen.
Oh, okay.
Here, so now all of a sudden, because I swap,
Yeah.
so, yeah, we're good now. Yeah, everywhere it's being presented. Now it is on my screen, so let me minimize this. Move it out of screen. And okay, all right, I am ready.
Hi, everyone. So, welcome. Hope you are all enjoying the wonderful weather. And the main goal of the charter is to promote operations. So we organize workshops and how to do it. And last year we also had so continuing with the seminar series, because we have Professor Anasori with us. So he is a writing star associate professor at the school material and chemical engineering at Purdue, the editor-in-chief of the graphene and 2D material, Printer Nature Journal. He received his PhD at Princeton University in 2014 in the material science department, the birthplace of MXenes. Dr. Anasori has more than 170 experience publication on and their precursors, and he is among the Web of Science highly cited researchers 20 times. He is also fourth on the 2023 list of rising stars of science in the USA by research.com. In 2023, he was identified by scholars GPS as the #1 mechanical engineer in USA in the past 5 years. He has received several international awards in 2016 Society COVID Award, the 2021 Drexel University 40 under 40, the 2021 Waterloo Rising Star Award in Nanoscience and Nanotechnology, and the 2024 English Award at ITU. Dr. Anasori staff work from developing novel 2D carbide and carbonitide mapping for various applications, including energy generation, electromagnetic interference. That please join me for today's professor.
Sure. Yeah.
Thank you.
All right, good. Well, good morning, everyone. Thank you so much for inviting me. On this side. Usually that's the way to present.
Yes.
But there are many classes podium is on the other side. But I'm to move around. So thank you so much for inviting me. This is really the highlight of any time with students. It is the highlight of my week, my month. So I'm so glad that I'm starting my week discussion and presentation to all of you here. As you probably know, today 2/3 of my time will be technical, my research, and then 1/3, the last part, we'll be talking about my career, basically work life, my perspective. My perspective. So feel free to stop me at questions at the end. Either way. So the focus of my talk today would be on these guys, MXenes. How many of you show of hand know word? Sure. Many of you can name one composition of MXenes. Okay, so you are in the right place. It's good talk because this is a large family that I'm going to talk about today. They're all available to all of you. Collaboration. So mainly focus on MXenes and then some hydrogen evolution reaction. In general, the scope of my lab, if I can move the slides.
I think there's one click needed.
Yes. Start. So the scope of my research focuses on novel discovery of materials, design, and fundamental understanding of materials in general. Okay, now the focus is on MXenes that I'm going to talk about today. Now, when we synthesize these nanomaterials, so we make these materials, basically are ingredients, raw material are the elements of the periodic table done in biolab. Sometimes we synthesize what we know, and sometimes we aim to discover, to design novel structures, new materials. When we synthesize these, in my lab, we have three directions in the applied machine. One is manufacturing, nanomanufacturing. The second is electrocatalysis, which is basically a portion of clean environment research. And the third area is extreme environments. And usually at the moment, extreme environments is ultra high temperature. So about 2000 degrees Celsius, 3000 degrees Celsius. For a variety of different applications, space is one. In general, anytime you pass, we go to different Mach, which is multiplying the speed of sound, other signs. We use the materials that can withstand ultra high temperature. So these are the three areas of research, but at the core is materials discovery. So today we're going to talk about materials discovery and electrocatalysis. We're going to leave these two parts out. So first, let me introduce MXenes. They are 2D transition metal carbides. So they are essentially, we can think of them as sheets of paper that are made of transition metals. Which transition? The ones on the left, meaning the early transition metals. Then in between every layers of metal, we have shove and of gravity. Okay, well, perfect. How many of you know how to make that? Okay. Yeah, I'm going to cover that. So here's a question. I want you to just show the number that your answer with your fingers. What year do you think MXenes were discovered? 1992. So number one. Then answer number two is 1998. Number three, 2004. Number four, 2008. 4, 3. Linear between 3 and 4. We had 1. So the right answer is we're just about to answer it for fun. So we're talking about 3D material. So the question is, do you know what year they were discovered? What year they were discovered? So 1992, 98, 2004, 2009. Just a yes. Yeah. Yes, that's correct. That is the right answer. So they were discovered in 2011, not long ago. Well, it depends on basically your age. I say not long ago, for example, from 2011 to now, changes happened in your life. So that's a long time ago. From 2024 to 2034, we graduated in basically more of the end of life. So if you look back 10 years ago, 2034 would be not long ago. So that's where my perspective is. Anyway, 13 years ago, MXenes were discovered at Drexel University in Philadelphia. They are one of the main 2D materials. If you look at the world of 2D materials, they all started after graphene, which the seminal paper came out in 2004. The literature before that actually characterized a single layer of carbon on graphene. Now, since then, there's massive number of different families, not just family of 2D materials. Transition metal dichalcogenides. How many of you are familiar with the transition metal dichalcogenides, or TMDs or TMDCs? Okay, so there's a close relationship in terms of understanding with MXenes or TMDCs. Just explain what they are. So it's 2, 3, 4, 5 layers of transition metals. Every 2 layers are interleaved with a layer of carbon. Now, since we have a metal on the surface, the metal has some available bonds, dangling bonds, that they are ready to bond to anything available. So that makes these called yellowish color, right? And they are, you call it the surface terminations. It can be oxygen, it can be fluorine. It can be synthesized. Now, just to make it clear, anytime you touch a metal or a metal carbide, as long as they are not oxide, you always have this layer, this yellow layer, like the oxide scale. That oxide layer always exists, unless you take the material, the metal carbide, to vacuum, then you don't have it. Now, when you're dealing with aluminum, you never say, well, it's aluminum with TX, because we show this 2 layers with T. Why? Because you're dealing with the bulk material. Million layers of atoms. Just 2 layers of oxygen. But when you have only 2, 3, 4, 5 layers of atoms, transition metal, then having 2 layers of oxygen or all of these surface species will play a major role in your properties. So they become part of the formula. So that's why we show the T, because now they play a major role in the properties, in the characteristics of these surfaces. So that's where we get these. So we have the M, which is the transition metal, X is carbon or nitrogen, and then we show T as surface terminations, surface species. So this is MXenes. How many of you know what MXenes are? Sure. Just some understanding of it. It didn't help? Based on this slide. Just want to see how, if I need to repeat it, I would be happy to do it. So this way is, think of a layer, sheets of paper made of 5 layers of atoms. And they are metal carbides. So anytime you want to think of MXenes, metal, at the thinnest level possible, about 1 nanometer. Now, how do we make them? In general, to make 2D materials, or in general, nanomaterials, we have 2 methods. To make something very small, we have 2 options. One is 1.1 is on that nanostructure. That is the bottom-up method. 1 by 1 atoms. That's how we make buildings, right? Bottom-up. The other method, which is a top-down method, meaning that first you have a block of material, then you slice it to get to break it to get to that. In MXenes, we only use the top-down method, meaning that we start with the bulk, then we exfoliate it into sheets. The famous example is graphite to graphene, which is just grain of graphite. All know, and so that as direct. And as direct, we exfoliate. If you manage to exfoliate to get to 1 layer, that was, something that all of us have done. Right? We all have written with pencil. I assume, yes. We're old enough to only sign that. So the real. So all exfoliated. But 2 scientists try to simulate, which was thought to be impossible, to characterize it to be two. Now, scope of MXene. Do you know why people thought that being a 2D material would be impossible? You know, we know that we have layers of matter, but people thought that if you want to just keep layer of matter, which is carbon, as a 2D, it is unstable. Do you know why? Exactly. People thought that this is just so costly in terms of energy that the system, nature does not want to keep this. If you have all of this layer, atoms of this layer, all compiled to one blob, then the surface energy is lower. So always, you know, the system wants to lower the energy. So people thought that, yes, there's something, the layer of carbon, but you can never have a single layer. But they, by they, I mean the two scientists, both Tunable solo, they managed a single layer and measure the electrical properties. Went to renewable physics only 6 years after the discovery in 2004. Following the same method, we use the top-down exfoliation to make MXene. Now, there is no titanium. You can never say, well, there was a time in my life that I using titanium. With carbides in your life. Oxide carbide from materials process. They are very hard. You ever drill something at home? Use a drill bit. Some of them are, they're so hard, nothing comes out of them, right? Unlike pencil, right? With carbide, you can do anything because they just have all the strong bonds between the layers. So this method doesn't work on just grabbing tungsten carbide and exploding it. Just ultra hard, very strong material. So to design a 2D carbide, you need to change the precursor that we cannot use tungsten carbide or titanium carbide. We need to make it in a way that it is layered and you have something weak between the layers. Because the reason that we can get this exfoliation is because we have these weak bonds between the layers. The van der Waals bonds between the layers are exfoliated. In carbide, we don't have that. They're all covalent ionic bonds. There's no way we can break them. We can just break everything, but we cannot really make the layers. So we need to design the precursor. This precursor is called a max phase, and I'm going to talk about it. As soon as we have this layer structure, we can exfoliate it. This method of top-down now being explored in a variety of different materials. And you see that 2D materials covers almost the majority of the periodic table. So you can have a 3D material with all these elements and choose when needed based on the desired property. So I put this periodic table here to draw your attention to you need material, you need high surface area, this element. There might be a 2D rate of that if MXene cannot solve it, which in most cases MXene can solve it. Might be biased. So how to make MXenes? As I said, you need a precursor that must be labeled. So that in that titanium carbide, tungsten carbide, now imagine that somehow we managed to put a layer, which is red here, that it is bonded to the metal, but in a weaker way. For example, if we are covalent, what is the weaker bond? Metallic. We managed to do that. Then we can selectively break those red to green bonds because they're weaker. Make these layered structure. Now we have the titanium carbide, which is layered. Between the layers, we have these secondary bonds, van der Waals bonds. And we know how to break them from early ages, right? Pencil. So when we have it in this form, MXenes are in solution. So all we do just shape the solution, get to this level, and make these 2D sheets. Here's single 2D sheet of MXene on TM grade transmission electron. It comes in a solution. We can filter all these 2D flakes. We can see the cross section here to make a film. Now let's learn a little bit more about the precursor. It's not a magic that we just put that red element. Those precursors are called MXenes. To synthesize them, for example, if you want to make a titanium carbide MXene, why I say titanium carbide? Because that's a well-known MXene that about 60-something% of the literature of MXene is focused on one combination. If you want to make that, all you need to do is first make this layer structure that has aluminum between the layers of MXenes. To make this, you just mix 3 moles of titanium, 1 mole of aluminum, 2 moles of carbon. Why? Because that's a formula. Mix it, put it in a furnace under inert gas, hold it at 1400 Celsius for 2 hours. Let's have this layer structure. This layer structure is not alone. We have more than 100 different max phases. What are max phases? We are familiar with the M, right? It's similar to MXenes. X is carbon and nitrogen. The A comes from the A group elements naming. And you can think of, for example, group 13 to 15 of the periodic table. The majority of all the maxes used for MXene are aluminum. So we can have 2 layers of titanium, then 1 layer of aluminum, or it can be vanadium, same thing, same structure with aluminum, or it can be 3 layers, it can be 4 layers, niobium, tantalum, all these elements of the periodic table. So now that we have the precursor, put it into selective etchant. What is a selective etchant? We use hydrofluoric acid. Hydrofluoric acid is very selective, and it only attacks at the beginning the aluminum layers, and the aluminum layers are being etched in the form of aluminum fluoride. They're out, and we get to MXenes. When we have these MXenes, so now if you say, well, I'm not interested in the synthesis, why have the issue of that? So my lab synthesizes all MXenes, and now take it and explore it in your interest. I'm happy to collaborate. So, what form can you get MXene? We can have it in powder form. This powder form, we can think of it as a but water, but so we can blade it, Dr. blade it to make a film, roll it to make a film, or you can exfoliate it. Remember, take this water and then agitate, mechanical shape, and you get single flakes. Now this solution is basically a paint, water-based solution that single flakes, 3D carbides, that you can spray desired surfaces, or you can filter it to make a film. As I said, if you look at here, number 1 is the precursor. So we study the precursor in my lab to see how we can control the properties of final MXene based off of the precursor. It's the same as if you have very defective graphite and very small particles, you cannot make a large sheet of graphite. It's defective because the graphite. So that's what we do in my lab. We look at how we can control the defects, how we can control the quality of MXene based off of the precursor. So we look at the fundamentals of MXene synthesis. This is, if you're interested to just know, get some idea of how MXenes are synthesized, I invite you to read this paper. If you just Google Scholar Fundamentals of MXene Synthesis, the title of the slide, we get to this paper. And first, we discuss how the precursors are made by diffusion. It can be diffusion of carbon into structures, or it can be diffusion of aluminum into titanium. Depending on what diffuses to what, how, here are some fibers, and you can see the core is carbon and the outer is titanium and aluminum entering. So these are partially synthesized. to just show that what we have visualized with the schematics, we actually have. Based off of what diffuses to what, the quality of MXene changes. So if you say, well, I can buy the MXenes at one, really depends how it's same composition, but you can get totally different behavior. This is basically the shelf life of MXene. And you can see that in many cases, after 10 days in water, they're gone. Store metal carbides in water, like water will attack. Now, if you have only 1 nanometer, it's easier for water to collide because you have 5 layers of atoms. But if you just enhance the quality of the precursor, the max phase, you can have it last for up to a month in water. So it really depends. Nothing else has changed here, just the precursor. Now, even we showed how to, if we clean, so even the process, it's not the synthesis, it's not the etching, it is just the how to clean the powder, that will affect the quality of MXene. You see, this is a single sheet of 2D on a membrane. It's a way to show it. So the membrane is more of a substrate. These holy area, these are the substrate, and you can see a single sheet. And depending on how we clean the powder, you can see that it's this one. You don't see any holes, but in the last one, you see a lot of holes. That's just because of how we process. And that will affect the quality, the stability. I'm going to skip through this. Now, the other area is how to etch it. I mentioned hydrofluoric acid. What concentration? If you add more concentration versus less concentration, that will control your number of defects. You know, when you have high surface area, having or not having atoms on the surface will play a role in almost all properties and application of your treatment. Now I'm going to talk about electrocatalysis, that everything is on the surface. So whether I'm missing few of the titanium atoms or not, that will have major effects on results. So here what we're showing here is basically hydrofluoric acid. If you keep it for longer, or if you increase the concentration of your hydrofluoric acid, HF is hydrofluoric acid. If you have 5.8% versus 9 versus 12.5, that will just change the number of defects. Look at this flake, the cross, so see all the atoms are there. Because this one only has less than 1 atomic percent titanium vacancy. So almost no missing atoms. But if I bump the concentration of acid to 9, you see some of the titanium atoms are gone. It's hydrofluoric acid that also attacks the titanium and removes that. That you can see that if you go to this one, the concentration of defects gets to around 9 atomic percent. So now 9% of atoms of titanium are missing. So if I increase the concentration even further, I can get to 16% of vacancies. This plot is, to me, very impressive. 2 reasons. Third one, first tell you, this is a very expensive. This is secondary ion mass spectrometry, which is basically, or acronym is SINGs. We have a lot of tough SINGs, time of flight SINGs, that basically the ion will just go raster and remove these, and there is something that analyzes what they get. Here is the dynamic spectrometry, meaning that it can do layer by layer. Now, to get these, every panel of these costs us $1,000. Instead of $3,000 here. So that's the third. Now, the 2 main points of this slide. So that was the cost. And also, I'm very impressed to just look at this level of accuracy. But the point here is, the method that now we're using is almost perfect See. No defects, which is very impressive because it's a top down. We're not designing atoms by atom. We put it into hydrofluoric acid. Then we do agitation, we do delamination, all those processes, and we are not losing any titanium, which is very impressive to me. And the second is high level of control over defects. For example, we have application, the reaction will happen, the electrochemistry reaction happens. Tell me, we need more defects, here are more defects. So if I give you the best MXene that we have, it might be the worst MXene. It doesn't have anything. So depending on the application, now we can control the number of defects to go to higher and higher. Also, if you say my reactions only happen at the edges, break the flakes. We have a 2D flake, we can break it into smaller pieces instead of having micron size to smaller pieces. This is much easier. Just sonicate it with ultrasound waves and break the 2D flake smaller and smaller. Because you say, well, the edges are the key. Okay. With more edges, meaning smaller flakes. Now, a random question. We don't know the answer, but let's see what. In electrocatalysis, do you think just are the sides for the electrocatalysis reaction, or do you think the entire basal plane are the actives? The edges are active or the basal plane. So let's see. Let's call this one number 1, number 2. Show of hand. Number 1, the basal plane. Number 2, the edges. Good. Okay, so the edges. That is the correct answer with regard to other keys. Transition metal dicap coagulants, TMDs, TMDCs, are active. However, since it's the opposite, it's entire basal plane. I would argue that if you want to make a 2D material, you better design it that the entire basal plane becomes active. Otherwise, you better make quantum dots, right? Because then you have more edges, right? You're going to make a 2D and then break it. So for MXenes, the basal plane, the entire 2D plane is electrochemically active. We know that all of these areas is active sites for electrocatalysis. I'll get to that in a minute. Now, here's some summary of MXenes. You say, well, I'm here, I'm not interested in electrochemistry, so let me give you some points to remember about MXenes. MXenes, they are hydrophilic, meaning that they're water-based. And anywhere you can paint, we can put MXenes. They have negative zeta potential. That's why we have these solutions being stable. So that ink is stable if you just leave it on your lab bench. It will not go down. It will not aggregate because every flake is negatively charged. So we have the electrostatic repulsion. High mechanical stiffness, obviously we have metal carbides. The electrical conductivity are, you can think of them as 2D metals. They have high electrical conductivity. How high? It's about an order of magnitude lower than copper. But it's kinds of process. If you make carbon nanotube of solution processing that you want to mix it, for example, with your active material to make an electrode, it will perform better. And because of the hydrophilicity, you can use MXenes to bind to make them studies. Use MXenes as active material in battery, or you can just mix it with your active material and eliminate all the other additives. Defined. Also, it's conductive. So you can also potentially eliminate your current collector and just use a MXene field. Now, because you're not using a metal, if you design it right, which is open project, then the impedance between your electrode and collector will be much lower. It can transport ions. That's why the majority of body of literature on MXenes are on energy storage. They can absorb a whole bunch of different molecules. The thickness of MXenes is about 1 nanometer, depending on how many layers. And lateral size, now you learn that it can be few nanometers to few. Here's a question for all of you. See how much. So you must know this answer. MXenes T3C2 is electrically conductive, insulating, or it's a semiconductor. Now, use one of these emojis. If it is conductive, insulating, or semiconductor. Sure. Okay. Glad that all of you are the same. Yes. Conductive is one of the key features of all 2D materials. Usually we are talking about semiconductor materials. When we talk about there are predictions of semiconductor MXenes, but we have not synthesized them. So anytime you think of MXenes, think of them as from the electrical conductivity as 2D metals. Okay. Moving forward, the MXene family. Here are all the applications. So till now, you can ask, so what? Okay. So what? So here are the applications. So you can see that a good portion is on energy, whether it is energy storage for batteries, supercapacitors. Then the next one is catalysis. There are OER, CO2 reduction, but I say that the main application would be HER, hydrogen electron reaction. Why? Then you see optics, electronics, mechanical, electromagnetic interference shielding, environment, and even biomedical application. For treating cancer, used for brain electrodes, a whole bunch of different applications. If you ask me, it doesn't need to be you, anyone asks me, what is the killer application of this? We had an interview 3 weeks ago on from chemical and energy, chemical and engineering news. CNBC. How many of you heard the same story? I'm with you. So there was a cover story about MXenes, and they interview a whole bunch of the pioneers. And when they asked him what is the killer application of MXene, I said, one, electromagnetic interference shielding. That's the one that will make it to the market within 1, let's see, 2 years. The second, in my opinion, which make MXene different than all other 2D materials, is electric catalysis. Biomedical, environment. So all these are shown outperforming other factors. These are the two. EMI shielding, electromagnetic, basically interacting with electromagnetic waves. Not going to cover at all today, then electric catalysis. In terms of composition, here's basically the boom of MXene in the past, since the discovery in 2011. The first one MXene being discovered was titanium carbide, T3C2. I'm not showing the TX here because it's just already too complex. So I'm dropping the TX. I'm just focusing on the transition metal and carbon. Now, in terms of structures, we all know that we can have a pure metal, or we can have we call it a salt solution. A salt solution basically means it is a solution of 2 elements in solid form. Okay. Now, but usually we refer to just pure metal, so that's why we call these salt solutions. Now, something very unique about MXenes is that sometimes when we mix certain transition metals, such as molybdenum and titanium, instead of forming an alloy, we mix sandwiches, layers. So we have, for example, layer of molybdenum in the outside and layer of titanium in the middle. Do we design it by layer? No, we rely on thermodynamics that makes this happen. There are some discoveries, for example, this one came out in 2021, so we're still doing more discoveries. This is basically made in my lab very recently, and we are working on about 17, based on my students' number, 17 new high entropy. What are entropies? Basically, the same salt solution idea that I mentioned, but instead of having 2 elements, we have 4 or more elements. These are not alloys, meaning that they're all equimolar, same number of moles. I'm going to skip through this. So basically, we synthesize them, and now there are a whole bunch of entropy maximum reported by other groups. We're not alone. So the answer, sometimes people ask, are we alone? I don't answer, but in the world of vaccine, we're not alone. There are more studies coming from Europe and Asia than the US, which is kind of sad because US. And but still, we have the majority of materials discovery happening in the US. It's not just research. You can see there are thousands of patents. There are companies, MoChA, LG, Samsung, and all working on it. So it's a new material, 13 years old, but there are companies licensing the patents. Now, let's jump really quick on the environmental. I'm going to briefly mention, and if you're more interested, we can chat more about the HER. My environmental clean environment is HER only, but there are a whole bunch of, clean environment can be electric catalysis, can be also environment, clean water, gas sensing, all of it. So now what we do, we look at the chemistry of MXenes and see how we can improve the electric catalysis. Working on novel phases. The hydrogen evolution of MXenes. I already answered this question. For transition metal dichalcogenides, usually the edges are active. The entire base of the entire 2D plane are electrocatalytically active, especially for HER, that can lead to hydrogen evolution reaction. Now, the first study came out in 2016 in ACS Energy Letters. We showed that the molybdenum carbide MXene has one of the lowest overpotential at around at 10 millivolt. Usually that's where we report it. 200 for molybdenum carbide MXene. Also, there are studies that we work on later in 2017 showing that if we change the outer layer and if we change the surface termination, while just changing the fluorine to oxygen, we can change the overpotential. So it's not only the transition metal, what we put on the surface of MXene will determine the or in general electrochemistry activity of MXene. So the surface termination, just focus on the transition metal, meaning just focus on what we have. So one question we asked was, can we control? So I said that the surface termination controls these elements, control the electrochemistry or electric catalysis. Now we ask, if we change the inner layers, we have this much of accuracy. If you change the inner layers, will that change the behavior of MXene for HER or not? Run through these slides. But yes, we showed that yes, if we change the inner layer, meaning we keep show it on the schematic. So if you keep the outer, we don't change the molybdenum layers, and we swap the inner layers from titanium, which is less HER active, to niobium, do we see any changes in behavior of MXene? The short answer, after we try a whole bunch of different compositions on the precursor and then study that, you see that these are just basically different composition going from molybdenum rich to niobium rich. We got to our answer, the lamination of that yes, if we, here's the over potential at 10 million, that when we have different ratio of molybdenum, it performs better than molybdenum titanium. When we don't have niobium in the layer, then we ask, how about the outer layers? So we showed that yes, molybdenum, if it stays and we change the inner, it changes. But if we change the molybdenum to something else, will that change? And the answer is yes. So here we looked at 3 different MXenes. The chromium titanium MXene, the outer layer is chromium, the molybdenum titanium, and the tungsten titanium. So here we finally arrived at tungsten. This study has not been published yet. So tungsten carbide, tungsten TiC2 does not exist in the literature, but it exists at Purdue. So hopefully soon everyone will learn about it. But that's basically, we are submitting the manuscript. When we switch, let's see what happens. So here's the titanium, HER. Here's the chromium, here's the molybdenum titanium, and here's the tungsten. For tungsten, we got to the lowest over potential for MXene. Skip through this. Basically, here are all the HER, all MXenes that we measured in our lab. This is not a literature review. These are all compositions measured for HER. HER is your thing. We can use this as basically a source. But the point of this slide is also the tunability of MXenes. I mentioned even in my item that we can play. It's the same family of material, MXenes, but we can play with the composition, going from titanium to tantalum to niobium, changing the number of layers, going to chromium, molybdenum, changing the number of layers, going to high entropy, then molybdenum, and finally tungsten titanium. And tune the properties. This is one example of it can be done for other electrochemistry applications or even beyond. So that's basically the technical part. What really I want to draw your attention to is the availability of MXenes. Here, any of these MXenes synthesized in my lab. So if you're interested, obviously, for any of these interests, please do click the picture review, see whether somebody has done it. If the answer is yes, because almost getting to 20,000 acres of MXenes, 17,000 at the moment. But not everybody tried it in all these compositions. The majority of that, as I said, 60-something% of all publications are done on titanium carbide. So we design something better with all these variety of compositions. That's basically my message, my technical. Before I finish, I want to draw your attention to this competition that I'm organizing through Purdue, which is called nano-orthography. This is a competition I started 8 years ago. It's international. All it takes is one microscope. It can be electron, it can be optical to win $1,000. First place win $1,000. Work on 2D materials. Graphene and 2D materials is the journal that I lead. So if you're interested, more than welcome to submit. Also, you know that postdocs, if you're interested in, send me an email, send me your CV, and I will, if I receive a manuscript that matches your background, I'll be happy to send it to you. So with that, I'll finish my technical. Few slides from career, so maybe I can jump on that. Yeah. Okay, so, but before I jump onto that, because it's another presentation, I want to just thank my research group, the fantastic students who do all the work, and I just get the joy of working with all of them.
So let me stop sharing here. And then okay.
I we have chance to ask technical question.
Yeah, it will be.
Yeah. It's up to you. Well, let's do after. It's been an hour that we've been sitting, so I asked all of you to rise just for to stand up, do some exercise. Yes. I personally, if I sit for more than an hour, I cannot concentrate, so it helps. You're welcome to stand or sit whenever you want. So what I want to talk about now is not technical, it's more of a personal perspective. Now, something I want all of you to pay attention to is all your panels as a goal. All of these are perspective. The technical part is not my perspective. Those are data results. This part, just my perspective. More than welcome to ignore all of it, or you take all of it. Remember, every time you see somebody talking about their career, don't say, well, this is the way to go down. Keep it back to something. So these are the points I'm going to take. Now, navigate your, there are many variables we all need to consider. Being observant, as I mentioned, just look and see everyone else's. Identify those who you admire, their work, style, achievements, lifestyle, anything, and try to some parts of their life. Work friends and colleagues are key. So pay attention. Soon you become like your friends and work friends, colleagues. Now you can just do this in ChatGPT, and it just gives you a whole bunch of different keyboards, as we all do these days. But my points are these three, and the next one is social media presence is highly recommended. Not Instagram, about LinkedIn at the moment. In the sense that maybe tomorrow, another Elon Musk will buy it and turn it into something like Twitter. It's here. At the moment, it's in social media. It is very helpful to standing network. We can interact with some folks without even meeting them, and then when you meet them at a conference, they can be open, they can be your future advisors, they can be your future bosses, and at the same time, don't get overwhelmed with social media. Meaning that other achievements doesn't mean that you need to achieve everyone else's achievement. That's then you are what you become. The worst thing you can do is you look around and say, well, this friend of mine got this, that, like that. Why am I not receiving any of these recognitions? So ignore all that. See, I'm interested in pursuing that. Receive that recognition. You student or something. Do your best to achieve it. If you get it, excellent. If you don't, enjoy the path. The other really scary thing to me is this victim personality influencers on social media. A lot, thankfully. Some folks come and complaining about it. Yeah, it makes sense, right? Why academia is like this? Why people are judged based on the quality of their papers? That's the only outcome. What else do you want to really basically evaluation? Or why the salary in academia is less than industry? You can't fix it. You cannot fix it. Focus on things that you can fix. So anytime you see somebody complains, check their background. See what they have done. They've done anything for anyone. If yes, look at those. If yes, just complain. Just avoid them as much as you just want. You know, like people talk, oh, Elon Musk quit. Well, let's talk about the good Elon Musk, right? You know, old Elon Musk. Really, he did a lot, even for EVs and making all the no patents, making everything open. But the point I want to make here is, well, academia is bad because he quit grad school. Well, that was just one example. Why you're focusing on one example? That was him, but he's the one that bought Twitter and did all these random things. Right? So you cannot just say, well, this person did not do grad school, so why should I? Because it is his path. It is not your path. So that's really the point I want to make clear. Find your authentic self. If you just hear this without thinking, it can be one. You receive because okay, what does it mean? Well, it is what you can do to get to authentic self is you need to be a collection of people and environments around you. Find 5 professors in the department that you like and look at their CV, their career path, and try to see what they did. Identify your role models. As I said, it can be in the department, your advisor, or it can be those who never interacted. But on social media, you see how they promote, for example, students, they talk about technical. Again, on social media, all of you will get your doctorates in engineering. You're not supposed to talk about psychology. That's my point. If I want to talk about work environment, I better just cite the paper, not just complain. Or show that, okay, we have this issue in our society and fix it this way. Show a solution. So these are the things that you can do to get to your authentic self. There's the point. Life can only be understood. Look at someone's life. This to get to here. No, maybe not. Just all this. At that time, they did not know what exactly they are going, where exactly they are going. So it's the same for you. You must live the life forward. Inspiration, but looking backward on someone else's life, but life, the beauty of life is you don't know where exactly going. For myself, I'm going to skip many of these, but basically that's my career. Teaching, building, fixing things, research in materials, and becoming a professor. My point here is that I'm going to skip through many of these, is that, well, let me give you a little bit of background about myself. I'm originally from Iran. I was born and I did my bachelor's and master's. Then moved to Philadelphia in 2009, to Indianapolis in 2019, and that's not my 23. My first jobs. Now, here's the things that you can define your authentic self. Pay attention to yourself. What do you really enjoy? For example, for me, I was a kid, really enjoyed exams. She was a high school teacher. It wasn't just one day. She asked me, "Are you interested?" Sure. I started grading. And since 10 years old, all the way to college, I was helping. I enjoyed it. So that was one key characteristic. So I thought, and then in high school, I started tutoring physics. Many of you are doing this. So when you do this, ask yourself, is it something that you want to do forever? The answer is yes, probably the answer can be. People say, not really sure. It's not the best for you. You've gone to classes and you think the professor is so smart that you don't understand anything. But that's the opposite. My job is to make any complex subject for you so easy that you understand. I like teaching. So, like teaching, become your professor is something. Teaching was something and you never get anything in return. Right? You write a paper, proposal, get funding, you get recognition. In teaching, usually you get student evaluation. Yeah, positive, always something. I'm lucky, usually I get positive reviews. So teaching, me after teaching class, I was really hyper after because of all the energy I was getting. So that's the key. Then research, you all know the drill. I started working on during my undergraduate, working in research lab, and I fell in love with that. And then I did my master's more, and then PhD, then postdoc. So I developed this love for mentorship, working on multiple projects, writing proposals, mainly in my postdoc time. If you were to ask me during my PhD, what do you want to do? Still, I was 50-50 industry or because I not like teaching, because just I could not really think of, okay, this is exactly what I want to do. I would be lying if I tell you. Now, at the end of my PhD, I was more doubtful because I wasn't sure whether doing all these things at the same time and many more is something I want to sign up for, because it is a lot of work. Yes, you can go industry, less work. But you need to identify what you love to do. So, yeah, teaching, love building things. Something I did not mention as a kid, always like fix things, break things apart, fix them. So that was basically the indication that research. And luckily I got to the research that I love. And then work in R&D project, by the way, and in a foundry, did not like it. Then here's the part that I want all of you to pay attention. More than 120 faculty applications. 4 interviews, 9 on-site interviews, 3 years of my faculty. It's not easy. Sometimes, usually, from luckier than one cycle, 1 year of job application, you get that position. So that's basically how I ended up here. What is also draw your attention to say of the 1, 2. Okay. So that's basically a secret to enjoy what you do. And that's my point, that we need to find the flow. You ever said or heard somebody say, don't distract me, I'm in this zone. You find where you shine, you enjoy so much that you forget about everything. If you have heard of runner's high, somebody runs, yes, that's flow. Basically. Why bring it up here? Because I believe that if you practice, PhD dissertations, doing experiments, you can get to the level of flow. It was challenging enough. It makes it. I would exactly tell you what I mean by it. If you get to flow, yes, it's a lot of work. For example, with being a professor, just nonstop, always behind. If I go to industry, will I get paid more? Maybe yes, but won't be. So that's what. Now, what is flow? How many of you are familiar with Maslow's hierarchy of needs? See, I'm talking about psychology, but basically, flow, this pyramid or hierarchy of needs, these are the basics that without them we won't be alive, and it gets so hard. Depends on where you live in the world. For example, sometimes you just can get all the basics, or you can get higher and higher. At the top is where we have the flow. Flow is a term that this psychologist, Mihai Csikszentmihalyi, came up with, And it's a mental state when a person is fully immersed in the present, the feeling of energized focus. How do you get to the flow? So here's a really nice chart. The skill level, challenge. Basically, challenge versus mastery. If you have a low level of challenge, but high level of skill, it would be more of a relaxation. Because it's not a challenge, right? The many jobs that then it's repeating something, right? Those are really more of a relaxation. If you go to high level of challenge and high level of skill level, that's where you get your flow. At the beginning of PhD, you have low level of skills and see what you have. Anxiety, right? It's normal because it's a challenge. But if you get to a high level of skill mastery, then you can get to the flow. So you need to be focused, concentrated, sense of ecstasy. Right? You really get to outside of every day. When you're working on in the lab, just on your PhD, on a paper. Because when you're writing it, you just realize like just connecting with that. With inner clarity, knowing what needs to be done when you are in the flow, you are highly skilled, knowing the activity is doable, right? It's high challenging, sense of timelessness, motivation. Now, the 3 steps that you need to do. One is mastery. Practice, practice, skill. Momentum. Little, small progress. You only need to solve it today or this month. It's all about the progress that you make. Mindfulness, focus. Our electronic devices, as much as they're helpful, they are distractions. So you need to focus. Find a way to focus that works for you. Here's a cartoon that shows color just to not look at the phone images. Mattering, know that your work matters. So these are basically the 3 main steps. More, but because of interest of time, I want to talk about happiness, but you won't need to continue or just.
I think we are a little short on that. Yeah. Actually, this is amazing. So maybe we can do a detailed session sometime. So again, it's very important for us to know all this.
Yes, as I said, these are all my perspective, not a solution. Yes.
Questions, so maybe.
Let me switch then my presentation. Because I assume that you have technical questions. Or if you have the other one, that's okay too. Yes. Yes.
That over potential graph, I didn't see a proper trend. Like for some materials, there is more carbon later. So how is over potential changing in those?
You're talking about, for example, here. Oh, here. So the number, basically, right? Because Ti3C2 means that we have 2 layers of carbon.
And 2 layers of carbon, 2 layers of ice. Now, the majority of HER comes from transition metal. We know that in the world of early transition metals, tungsten and molybdenum are the best. Even if you look at the literature on tungsten carbide, the first paper that ever published about tungsten carbide in journal Science was on HER of tungsten carbide in 1971, not MXenes, just bulk. But they show that it has very low over potential. So it's mainly on the transition metal. Now, so first is the composition. See molybdenum, tungsten. We have high entropy, which is different. I'm not going to talk about high entropy right now because it just makes it too complex. So tungsten, molybdenum. Now, what is inner? Niobium, better than titanium. And after molybdenum, we have vanadium, chromium, then here, not as active as vanadium, only a handful of titanium. So these are transition metals. Now, if you just focus on these two, Ti3C2 versus Ti2C. Here we have 2 layers of titanium. Here Ti2C shows slightly better, fewer number of layers of atoms. So it is more about fewer number of atoms, which makes the electrons more available. Did I answer your question? Yes. So now it's not about impurities, because the reason that we made this plot, because if we gather data points from literature, somebody might synthesize in a different way. And as you mentioned, maybe they had some impurities or some carbon left. So to eliminate all those questions, we synthesized all of these my postdoc, obviously. She synthesized all these MXenes herself, just to make sure that everything is the same in terms of impurities or surface, even through the same process that we get the same surface species, surface termination. So the main changes that come is because of tungsten, just the transition metal tungsten versus pure titanium. So addition of tungsten, we knew from day one that if we can ever make, the first in 2014 was, if we can ever make a molybdenum, we'll be golden. And in 2016, that led to the discovery during my postdoc of all these phases, because we want to make the molybdenum. In parallel, other groups also made molybdenum. So we got the molybdenum because we knew that molybdenum carbide has the lowest over potential if you can make it. And it was basically motivation behind this. Since then, we said, well, if we can make tungsten, it would be even lower, because just based on the number of electrons, how tungsten carbides interacts in water splitting reaction versus molybdenum, it is performing the best. So as we go basically to the right of the transition metal groups groups, we get more activity, right? But tungsten is the last one in the MXene. But no one could ever make this one because there is no precursor available. We finally managed to make this one. I did not cover how because of the interest of time, but short answer is it's because of the transition metal. The bonding, the number of electrons that makes tungsten more active than titanium. So one is, these are carbides, right? So why I say hydrogen evolution reaction, because we go to reducing voltages. So we know it is stable. Now, as soon as if you ever keep it without reducing potential, take it to positive, MXenes carbides in general will get oxidized. So that's number one. Then we are doing it in aqueous. For all of these are, sulfuric acid aqueous. So with that, the water will kill MXene also because of hydrolysis. So we need to design them. So these are, something that we need to pay attention. Yes, these are valid data points, but to scale it up, we need to pay attention to stability of MXene as number one. Change the electrolyte, change the environment. But if what we do for all of these is just a drop casting of MXene solution on glassy carbon, no binder, nothing. That's easy. The second point is scalability. That's another part of my research group in my lab that we work on. We have figured out how to scale up this one. We've been working on this one for now 13 years. Now, everything new will go through the same
R&D in research groups. This one, we can only make it in small quantities, meaning gram batches, which is a lot for a nanomaterial, but it's not like kilogram batches like this. So scaling is another one compared to platinum that we need to work. If we identify, here's the best, which is tungsten right now, we need to identify a path that we can scale it up and make it stable. Yes.
So when we synthesize MXenes, introduce in your is that for avoiding yeah. And if we make oxide, can we make oxide MXenes if we have the same
That's an excellent question. So that's something that, you know, I personally love to work on, which is materials discovery, right? So we always ask these types of questions. How can we change while we're maintaining the properties? Now, by definition, MXenes are carbides and nitrides, not oxides. Because in general, when you're looking at the periodic table, boron, carbon, nitrogen, oxygen, fluorine. As we go to the right, electronegativity comes higher and higher. So oxygen will never form the covalent ionic bond that carbon and nitrogen make. It will be just purely ionic. So it will be a different structure.
so it won't be MXenes.
It won't be MXene. However, and here's the really interesting part. We now know, and that's why we see like partially gray, because now we know that because nothing is perfect in this world, right? I always talk about materials, and when I teach to mechanical engineering seniors or even in materials, I ask them that, are you looking for a perfect partner? That's now second part of my talk today. Perfect partner for life or an imperfect partner? Which one do you think? Which one? Imperfect, yes. Yeah, we don't call it, but I want to exactly no. I said that because I want to emphasize that nothing is perfect in this world, right? Everything has flaws. And those are the beauty of life, right? A perfect material, for example, if you have a perfect material, you cannot even deform it. It would just shatter. Right? So if you look at the stress strain curve, it would just have the catastrophic failure. It would be the same in life. If you have imperfection, it would be some yield and then plastic deformation, make the life much better. It's the same for materials. Now, coming back to your question, nothing is perfect. Now we know that we have some oxygen in the carbon lattice, in the carbon sublattice. So it can be up to 20% of all these carbons replaced by oxygen. Why? Well, we found this after 7 years of research on that. Because if you try to keep it up here, still have some so if I want to be technical, some not 50% oxygen, 5, 10%, 20%. In that black, one that should be that you have less than 1% atomic defects. So
we can control it up to maybe 20-25% of oxygen and keep it as maximum. But you cannot do that without the inert gas, because if you don't use inert gas, you burn everything. That's fire, basically. So everything will just purely become an oxide, no carbon, and you won't have the maximum. But if you look at the top plot, there are 2D oxides available. So if you don't want to go the MXene route, there are 2D oxides that you can synthesize. We are working on some equivalent structures of oxides to MXenes that we don't have a carbon, we only have oxygen, but we still have the surface termination. That would be a transition metal oxy halide, making 2D out of those. They are not MXenes, but they're 2D materials. They're more stable than carbides in water. And we don't need to worry about their oxidation, but we know that they won't be conductive, electrically conductive, because oxygen grabs onto all of the electrons so tight that there won't be any electron to move, make this conductive. It's the carbon and nitrogen that makes it conductive. So there are some gains and then you lose some.
How do you control high temperature to the MXene?
Okay, that's a question that if you ask anyone else, they probably have to answer, because that's one of the research we work on. Even when we started working on high temperature, so on the surface, the yellow, but we showed that that is not true. We can keep that seed fresh. About 1,000 nothing. Yeah, fire. Beyond 1,200, we won't turn to the oxide. What will happen is these layers will just fuse together, and you go from the 2D titanium carbide to the tungsten carbide. The tungsten carbide. So, 1,200 seconds later, beyond that, field remain as any other right now, the vortex stable maximum is about 600. To be almost double, maybe 800. We showed that now they are stable, just wrong laptop. Just because of control of the defects that I mentioned. Control of defects. When we work on this maximum. As we go to more defects, the stability temperature range. Sure. Yeah. Now, I don't have for all of you, but I have a few copies for any of you who are interested in nanoartography. If you want to learn how to win $1,000, I have a few copies that will leave them here for you to grab. Sure.
I was just curious about that particular slide of the defects, because you can tune how many defects that are present. My question is, what kind of property changes do you observe when you started to play around with the defects? More specifically, like activity, reactivity.
Conductivity will go down as we introduce more defects. As we remove titanium, conductivity will go down. Reactivity depends what type of reaction. For example, oxidation. We know that as you remove more titanium, it becomes more reactive with oxygen. It will basically degrade much faster.